All right, so let us remind ourselves just what it even means when we graph the way we've been graphing for years and years and years. Okay? So when you have graphed, okay, you've graphed on an XY plane, and we call this the Cartesian coordinate plane. If you didn't know that was the name of the thing you've been graphing on for years, it's named after René Descartes. And you may not have heard this before, but it is also referred to as rectangular, right? The rectangular plane. And that's where we have our x-axis and our y-axis. We have positives going in one direction, negatives going in the other direction. And this plane allows us to give information to others about location. And so, if I have a point and it's right there, I can pretty much universally tell people, internationally, I can tell them where point A is. I say point A is at 3, 4. And everybody in the world will know exactly where to go. Because our Cartesian coordinate plane says that we graph ordered pairs x, y, and that x represents, well, you start at the origin, and x represents moving horizontally 3 units like that, and then y represents moving vertically 4 units like that. And so these are directions to anybody. Go right 3, go up 4, and you will be at the right spot. We have other ways of communicating location, like we use latitude and longitude for locations. That's another method. But now in math, we have another method that is called polar coordinates. So when we talk about polar coordinates, we don't have an XY plane anymore. What we do have is we have a starting point here, which is called the pole, thus the name polar. And then from the pole, you start this direction and you measure an angle going counterclockwise. So you measure a directional angle, theta. And then you say, if here's theta, and so you're going to go along the path of theta, and then it's going to tell you how far up to go. Well, that idea of having a directional angle and a length, that's exactly what we did with vectors, right? Because vectors have direction and magnitude. So I love polar coordinates because it kind of brings together all this math stuff that we know. So back to my coordinate plane. I can go here, x, y, but I can also tell you how to get to point A using polar coordinates. And my polar coordinates are going to tell you what theta is and what r is. R is like the magnitude of that vector. It's this distance, it's this length. Now, when we do our ordered pair in polar coordinates, we put r first and then theta. So one thing we'd like to know is, well, if something is at point 3,4 on the Cartesian coordinate plane, how would we give that same location in polar coordinates? So in other words, if I know x is 3 and y is 4, how would I figure out r and theta? Well, guys, we did that with vectors already. If I want to know r, isn't r the magnitude of that vector? And we talked about the fact that you have a right triangle here. And so the magnitude of that vector is the square root of x squared plus y squared. Just like magnitude of a vector. So for this particular problem, r would be equal to the square root of 3 squared plus 4 squared, which means r would be the square root of 25, which means r would be 5. Now, when we learned about vectors, we also learned how to find this directional angle. So if you recall, we said, hey, we've got a right triangle. So let's think about trigonometry. SOHCAHTOA. And if this is my angle theta, y is my opposite, and x is my adjacent. Opposite and adjacent, that's the tangent relationship. So it is true that tangent of theta is going to equal y over x, because that's opposite over adjacent. So in this particular case, we would have tangent of theta equals 4 over 3. We would then take the inverse tangent of both sides. For that, we would use a calculator. And we would say inverse tangent of 4 divided by 3. And so theta would be equal to 53.13 degrees. So what this tells us is that if I have this point A, it's right here, this location, and it's at 3,4, so I could tell somebody, get to point A by going horizontally 3 and vertically 4, and you will land there. But I could also tell somebody in polar coordinates to do 5 and then 53.13 degrees, and you will get there. And these are the measurements used by submarines and airplanes, because up in the sky or down in the ocean, there's not really a coordinate plane to map things with. So in polar coordinates, all you have to do is anchor the pole somewhere, and then you can give your coordinates. So the way we graph in polar coordinates, even though the angle comes second, we would start here and we would go out to 53.13 degrees, and then we say now we're somewhere on this path, and we would go on this path until we got out to 5. And then boom, we'd land. Now, how are you going to know where the 5 is on here? Because one of the joys of the Cartesian coordinate plane is, you've got these little markers. So when we graph in polar coordinates, our plane looks like this, right? So we've got our horizontal piece. I'm going to draw a vertical one. So I'm going to go out for a radius of 1, radius of 1, radius of 1, radius of 1, and make a circle. And then I'm going to go radius of 2, radius of 2, radius of 2, radius of 2, and then make a circle. right? A circle is all the points that are equidistant from the center. Then I'd go out to radius 3, radius 3, radius 3, radius 3, and I'd make a circle. So have you ever seen in the movies where there's been an airplane or a submarine and that person has something that looks like this on their control panel? That's polar coordinates. So this 5 is going to go pretty far. So let's graph a different one. Let's say I wanted to graph 2 45 degrees. So the first thing I would do is say, where's 45 degrees? And we know that 45 degrees is half of 90 degrees. We all know that this is 90 degrees. So 45 degrees, right, comes right through here. So my angle is 45 degrees, and then my radius is 2. So there's a radius of 1, and a radius of 2 is right there. So if this was point B, there's where point B is. That's a very good question, Braden, and I'm not certain of the answer, how they establish the pole. I believe that the pole is their current location, but I am not 100% sure of that. If anybody has someone in their family who does piloting or drives a submarine, they may be able to tell us a little bit more, or I'm sure we could Google it. All right, so what if I wanted to graph the point 3, 225 degrees? So again, I'm going to measure counterclockwise. Here's 90, here's 180, and hopefully from your unit circle, you're used to thinking, oh, 225, that's 45 degrees past 180, right? So we're going out this way. This direction, so the 225 gives you your direction, and then how far out are you? You're out a radius of 3. 1, 2, 3. So if this is point C, it would be like that. Now, here are some interesting things that come into play with polar coordinates. On our Cartesian coordinate system, there's always only one answer, right? If you're up here at point A, where is point A? 3, 4. Well, where else is point A? No, 3, 4. That's it. It's at 3, 4. I mean, I guess you could say it's at like, you could say, oh, it's at 4 minus 1, because that's 3, and 5 minus 1. I mean, you could get creative with how to say 3 and 4, but it's at 3, 4. But because angles go around and around and around in a circle, I have more than one way to say where point B is. Point B is at 2 45 degrees. But what if I was at 2 405 degrees? Isn't that going to mean go around 360 and then 45 more and then go to a radius of 2? You're going to land right there on point B again, right? So there are actually infinite ways to get to point B. Anytime I have a radius of 2, And anytime my angle is 45 degrees plus a multiple of 360 degrees, I will land on point B. All right, but here's another tricky thing about polar coordinates, which is, what if I had the point -2, 225 degrees? All right, so that's going to mean go around 225 degrees. So I've gone around that much. Now my radius is -2. That means go 2 units in the opposite direction. 1, 2. That is also point B. See how that went? 225 degrees, right, around your pole, but instead of doing a radius of 2, 1, 2, you have to go, your radius has to go backwards, 1, 2. All right, so that's graphing polar coordinates, r, theta. Now let's go back up here to this one on the top. What if I had r theta and I wanted to change it over to rectangular coordinates? Well, that's really very simple. We already know all about this, right? So if I'm on polar and I want to go to rectangular, so in other words, I know what r and theta already are, and I'm trying to figure out what x and y are. Well, if I know r and theta and I'm trying to figure out x, that's right triangle trigonometry again, right? SOHCAHTOA. So let's say I want to know x. X is my adjacent, r is my hypotenuse. Adjacent and hypotenuse is cosine. So cosine of theta equals x over r. Then just times both sides by r. So r cosine theta, that's what x is. All right, how am I going to find the y value? Well, again, right triangle trig, here's theta, y is opposite. So opposite over hypotenuse, opposite and hypotenuse, that's your sine function. So cosine theta equals y over r, opposite over hypotenuse. So then simply multiply by r, and r cosine theta is y. So that's how you take a polar coordinate, change it back into rectangular. The coolest part to me, though, is about the graphing. And we've graphed points, but then next, well, I guess actually I'll see you guys on Friday, so even my seniors, you'll start to see that when we graph in the polar coordinate system, it makes really pretty pictures. Those of you that are into art, you'll be like an amazing connection between math and art. All right.